Okay, cool. Hey everyone, this is Wi-Fi talk. Um, just some Wi-Fi basics, and then mostly Wi-Fi crypto with WPA2. So I'm gonna first just talk about like a basic, your typical network configuration that you see Wi-Fi on, at least in a home. Uh, some very light software stuff, just OSI model. Uh, and then move into authenticating clients and encrypting data on the being sent over Wi-Fi. Mostly going to focus on WPA2 and the various modes of WPA2. I'm going to stick to the more popular ones. Wi-Fi is very, very complicated, so I'm not even going to cover that much. Um, and there's some crypto stuff that I'm gonna talk about. If you have questions, you can ask, and I can go into more detail. Um, yeah, cool. What is Wi-Fi? It's just a way to connect computers to the internet, or specifically to a network. Um, doesn't look like that. So cell phones, they connect to towers, and the towers connect to the internet. Cell phones operate over pretty long range, several miles. Wi-Fi is much, much lower powered, so it's only going to work, uh, on the order of yards. So in a typical home, uh, you're going to have a computer you want to connect to the internet. So then you attach a modem. The modem takes IP packets and then turns them into stuff the ISP understands. Typically, that used to be the phone line. Now it's often cable. It's really specific to where you live, but it's probably something to do with TV or phone, unless you have a dedicated fiber optic line. And then you have a router that connects to the modem, and the router just takes packets coming from one device and forwards them to the next device. And then you have a switch. The switch allows multiple devices to connect to that router. It sort of creates the router creates the network, but the switch allows you to join multiple cables over Ethernet probably. Um, and you can connect computers directly to the switch, but then what a lot of people do is they stick in an access point, and the access point is what actually does the Wi-Fi stuff. So the access point is responsible for decoding and encoding radio waves, and then your computer also has a chip on board that'll decode and encode data into radio waves. Um, a lot of home devices will combine the access point, switch, and router into a single box, and then sometimes they'll also combine the modem into a larger box. But for this talk, we're going to be talking about the client, which is also called a supplicant, or also the supplicant also refers to the software handling the Wi-Fi. The access point, and that's about it. The access point will then somehow connect to the network, but we're just focusing on the Wi-Fi part. So this is the bottom four layers of the OSI model. Wi-Fi, well, the radio waves are on the physical layer, but the actual frames and stuff that you can see in Wireshark and the stuff that the network card works with just before it, turns them into radio waves is at the data link layer. This is below the IP layer, so IP addresses are not something that you can use to identify devices when first connecting to Wi-Fi. So, I mean, just like with an Ethernet connection, use MAC addresses to identify devices. They're 6 bytes long. Wi-Fi card has a MAC address assigned to it. Companies typically could assign the first 3 bytes. That's Apple's, or those 3 bytes are used by Apple. Apple has a bunch of them. The 3 bytes in the example on screen. The access point uses the MAC address to identify your device. So if you ever connect to like hotel Wi-Fi and then they send you to that login page before you can access the internet, and then you like agree to the terms of services. What it's doing there is it's whitelisting your MAC address. MAC addresses are actually very lousy for security because they're being broadcast everywhere. So you could actually find someone's MAC address and spoof it, and get past that, get past the terms of service screen, or sometimes it's a login page. More generally, that's called a captive portal. But yeah, MAC addresses are used for identifying the access point as well as the client, and it's the unique identifier that's used in Wi-Fi.
When you say that MAC addresses are sent out all the time, is that like only in those cases where we're verifying with some like access control mechanism, or is it like with every bit of communication?
It's with every sort of Wi-Fi frame. Uh,
Okay, cool. Yeah, bit was a
uh,
bad like framing of that, but yeah, okay, that makes sense. Thank you.
yeah, because the router has to know where it's coming from and where it's going to. So if
Totally.
you and actually that's, I mean, MAC addresses aren't unique to Wi-Fi. They're also they're on Ethernet, but when you do an Ethernet connection or like a wide or some other wired connection, uh, but they're often specifically used for some Wi-Fi scenarios. So what makes Wi-Fi interesting? Well, a lot of things, but with Wi-Fi, you're broadcasting signals for everyone to see in your physical vicinity. You don't need to be on the network to see those signals. So if you have an Ethernet connection to a switch, somebody else needs to be jacked into that switch or hub to be able to see all your traffic, or they need to have a physical sort of interception device on the wire. Whereas Wi-Fi is a radio signal that sort of leaks everywhere. It'll go out of buildings. It's just anyone within the vicinity or with a very strong antenna. Uh, if they can see the signal, then they can see what you're broadcasting. So if you just encode data into radio waves and broadcast it, all you need to be able to do is decode that radio wave, and you can see what people are saying. And every Wi-Fi card is capable of that. That's how the Wi-Fi card works. So the Wi-Fi card is responsible for decoding and encoding radio signals. So we need encryption and authentication to prevent unwanted users from joining access points, as well as preventing anyone from seeing the content of the data being passed around. So I did a packet capture. I set up like a mini network. This is in Wireshark. So there are network cards that you can use to capture packets. For like sanity purposes, most network cards will discard packets that are not intended for you. But some network cards, you can actually turn that off, and you can actually capture every single thing that the network card sees on that frequency. It depends on the network card. There's like a list on certain Linux forums of Wi-Fi chipsets that'll be able to do that. It's called switching into monitor mode, or sometimes promiscuous mode. So I've done that here. I've set up an access point, and I've recorded it on Wireshark, and you can see these broadcast frames being sent out, and you can see the SSID as ISS as demo network. So the access point is constantly sending out pings. Well, in most cases, access points are constantly sending out pings, and your device will see these pings and then know that there's a Wi-Fi network nearby. So this is a capture of my phone trying to connect. This is a open network. It had no encryption on it. It's just the no password version of Wi-Fi. You can see that uh, you can see the frames that get exchanged. Um, but most importantly, you can see that ICMPv6 type, which is an IP packet for IPv6 pings. So that's at the IP layer. So what that shows is that uh, I mean, Wireshark didn't have access to any. I mean, there were no passwords used on this network, so you can just by being in the proximity, fairly easily capture all traffic from a network that doesn't use encryption. So now we're going to talk about crypto and specifically for encryption and authentication schemes. There are several types available. So for Wi-Fi, there's you can run an open network that doesn't require password or any sort of authentication. Um, Typically, that's seen as bad. I mean, it leaks information. WEP is a very, very old standard from like before 2004. Uh, it's really, really broken. Uh, I don't think I haven't seen anyone. I don't think anyone uses it anymore. Um, it's completely compromised. With like a pretty cheap laptop and a few minutes, you can break into a WP network. Um, WPA was used during the transition from WP to WPA2. Nobody really uses it much anymore. It's usually WPA2 that's being used, and then probably a few years ago, WPA3 was standardized. WPA2 has several problems that WPA3 addresses. Um, they both have modes for called PSK mode, which stands for pre-shared key. That's typically used in home networks where you just enter a password. And then they also have an enterprise mode, which allows people to have more complicated authentication systems. UT, for example, well, UT uses both. The UT IoT network uses the PSK mode, but your typical the UT Wi-Fi network that most people use, where you have to enter a username and password, that's using WPA2 Enterprise. WPA3 is so new that there's very little support for it. But WPA3 actually also has a mode where you can go passwordless, if I remember correctly, but it still uses encryption. So in this talk, I'm going to be talking about WPA2, both the PSK and Enterprise mode. And yeah, so WPA2 comes in two flavors. Uh, flavors. Pre-shared key is the one that most people use with a password, and then enterprise is used in small businesses and universities. And the reason it's separate is because you need to have an authentication server, which I'll get to later, uh, to handle connections. But it allows you to give different encryption keys to every single device, and also use a central database, authentication database to let people in. So UT, for example, can tie your EID to the Wi-Fi network, and when you update your EID, your Wi-Fi password will update as well. Okay, so there's a lot of diagrams on here, but basically, WPA2 encrypts um, data using 128-bit AES, and it's running in CCM mode. So CCM mode is AES with authentication. So you can verify that data hasn't been tampered with as well as encrypting it. Just AES on its own doesn't give you the ability to verify that data hasn't been tampered with. So I don't want to get into, unless somebody really wants to, I don't want to get into the block cipher details, but they're on this slide. Yeah, so it's just a symmetric key cryptography. for encrypting the bulk of the data. But for that to work, you have to have shared keys between the access point and the supplicants on the network. So WPA has uh, two keys actually. So it has a PTK, a pairwise transient key, and a GTK, group temporal key. The PTK is used for communications between the supplicant and the access point, and vice versa. And for multicast communication, where devices are communicating with each other directly on the network, you can do that over Wi-Fi, and there's a key that all the devices share, uh, called the group key. So to establish these keys, there's a four-way handshake that occurs at the beginning of every WPA2 session. So when your device first connects uh, over WPA2, there's a message sent from the AP to there'll be a diagram later. But the four-way handshake requires a shared initial secret, and then it derives the PTK and the GTK um, through the handshake. An important thing about the four-way handshake is that that shared initial secret, also known as the pre-master key, or pairwise master key, the PMK, isn't transmitted at any point. So anyone intercepting traffic will not see the pairwise master key. So STA here is short for station, and AP is access point. So the access point sends a random number to the station. The station is the client, which is known as a nonce. The idea of the nonce is that it's never supposed to be, it's random and you're never supposed to use it twice. And the client sends a nonce back to the station. While it does that, it's also constructing the PTK, and it uses the PTK to generate an authentication code that can only be generated by someone with the PTK, and that's the MIC. So it sends the S nonce and the MIC to the AP, and then the access point constructs the PTK because you need both nonces and the MAC addresses of the AP and the client, as well as the pairwise master key to generate the PTK. And then the access point has the group keys. You can't just generate the group key on fly because every single device on the network needs to have the same group key. So the access point maintains those group keys, and it sends it back to the client. The MIC, the authentication code there is to assure the client that the access point is really the access point. And then the client sends back an acknowledgement telling the access point that it's received the group key. Oh, the other thing about the four-way handshake that's important to note is that both the access point and the client have to know the pairwise master key. Otherwise, they will end up with different encryption keys and won't be able to communicate with each other. So this assures the access point that the client is really authorized on the network, but it also assures the client that the access point is a valid access point. What this prevents people from doing is from, without knowing the password, creating their own access point with the same name and then tricking people into connecting to that. Right, so this is a capture of a four-way handshake. It's on the same network, but then I turned on WPA2. And then you can see the key information bits that are numbered according to the part of the handshake it's from. So the first message contains the nonce from the access point and to the client. It contains no other data. And the second message contains the nonce from the client to the access point. And at this point, the client has also generated the pairwise transient key, and it also sends some key data as well as the MIC to the client, to the access point. Then the access point sends back its nonce again. It doesn't have to, but it does. And then there's the authentication code here, and then this key data contains the group key. And then this is just an ACK sent by the client to the access point to tell it that it's received the group key. Really, the only thing here is the authentication code.
What does MIC stand for?
I actually don't remember.
Okay.
There's like a ton of abbreviations and acronyms used all over Wi-Fi. So the MIC is generated by using a key, and so when I say PTK, the PTK is actually like uh, a large chunk of key that's split into smaller keys, and one of those keys is used to generate the MIC. But I don't know what MIC stands for.
Okay, that makes sense. Thanks.
Right. So still haven't discussed how to come up with the PMK, the pairwise master key, I think. Uh, it's a shared, so in PSK mode, you have a password that's shared between all the clients and the access point as well. And so the PSK, which is where the name of the mode comes from, is a key itself, and it's derived from the passphrase that you enter. So that passphrase is represented as ASCII text, and then it's put into the key derivation function called PBKDF2, which key derivation functions are designed to take in sort of arbitrary data, specifically passwords in this case, and then turn them into key material. Because when you generate a password, typically it doesn't have like an even distribution of randomness, and something like PBKDF2 generates a key that's more random from that initial passphrase. The SSID of the network is used as a salt, so two networks with the same passphrase but with different SSIDs will have different PSKs. It does 4096 iterations. That's part of the spec. That means it probably does HMAC about 4,000 times, and then it uses HMAC with SHA-1 as the PRF, the random function used in the key derivation function. Oh, and also it outputs 256 bits because the PSK is 256 bits. And then the PSK is the PMK in PSK mode. And so that's used as the input for the four-way handshake. So both the access point and the clients are aware of the password, and then they derive the PSK, which is the PMK, and then they go through the four-way handshake to generate the PTK, and then the access point sends over the GTK. Weak PSKs, so a weak PSK would be a PSK that comes from like a weak passphrase. If you have like an easily guessable passphrase, an attacker can sort of guess these things offline. If anyone captures a four-way handshake, which you can do if a client joins the network, you can capture a four-way handshake. By using the parameters in the four-way handshake, you can guess different passwords and see which ones are right without actually trying to connect to the network. So you can do this completely passively and guess a ton of passwords offline. You can accelerate it with GPU. You can rent stuff on the cloud. So weak passwords can be cracked. So this is actually a problem with WPA2 that gets fixed in WPA3. Oh, the other problem with PSK mode in particular is that all the clients have the same password, so they follow the same steps to generate the same. They follow the same steps to generate different encryption keys because the nonces will be different, so the PTKs will be different. But if any client is on the network and it captures the four-way handshake, it has enough information to decrypt the traffic of another client. So for example, on UT's network, if they used PSK mode, you could see everyone else's traffic uh, if you captured the four-way handshake. So enterprise exists to fix some of those problems and provide more flexibility. Um, it, the name of the standard, I think, is called 802.1x. It's a for authentication. So it's kind of complicated, but uh, it offloads that complicatedness to an authentication server. So a lot of home routers can work with enterprise. You need to have a server to handle that authentication, though. So the authenticator, also known as an access point, communicates with the authentication server on behalf of the client. So Radius is an IP level protocol. So the authenticator and the authentication server have to be on the same network and able to see each other, and they can communicate via IP, whereas the supplicant will be communicating to the authenticator via, the Wi-Fi protocols, and specifically EAP, which stands for Extensible Authentication Protocol, is used. Um, so, oh, the other thing the authentication server can do, in addition to authentication, is Radius supports accounting information, so you can keep track of network usage, and that can be used in situations for like billing clients for their network usage. So all of that is tracked to the authentication server, and the access point is just an intermediary for clients to authenticate. So this is just a diagram of what happens, but EAP is very, well, as it says in the name, extensible. So it's more of a framework rather than a specific protocol because there's many different types, and so I'll be talking about one later. Um, but you have requests and responses for AP going between the supplicant and authenticator, and then the authenticator is talking to the server via Radius. So here we go, more acronyms. PAP is Protected Extensible Authentication Protocol. So this mode, PAP with MS Chat, is very, very popular. It's what UT uses. It essentially allows you to connect to a network with a username and password. And then the server will have a database of usernames and passwords. So EAP on its own was designed for physical connections. So it has no security and it has no authentication. So PEAP is an extension to that wraps EAP in TLS, which is the same encryption protocol used for connecting to HTTPS sites. So the access point will actually have a certificate, and it'll show the client the certificate, and the client is supposed to check the certificate to make sure that's the correct access point. And then it'll set up an encrypted tunnel using TLS, at which point so you can add another EAP protocol on it, and in this case it would be MS-CHAP, which is something developed by Microsoft a long time ago. And basically it takes a username and a password, and it authenticates the client. It also authenticates the access point because MS-CHAP has mutual authentication, so both the access point and the client, actually both the Radius server and the client, would have to know the password. Otherwise, the client should reject the access point, or the access point should reject the client. MS-CHAP is really broken. It takes at most 2 to the 56 DES encryption operations to figure out the network key. And they don't have to know the password. They have to know the NTLM hash of the password. That's just a specific detail, but technically you don't need the password to log into the network. You really need the hash of it. But MS-CHAP is is broken, but it should be fine once you wrap it in PAP because TLS is not broken. Um, except except there's an assumption that TLS makes uh, where you have to check the certificate. When you go to a website, you see the lock icon. The certificate is being verified by your device. Um, for PAP, when you connect to a Wi-Fi network, you're supposed to verify a certificate, except it turns out uh, a lot of devices have a terrible way of verifying certificates. So when you go to a website, you check the domain name, and you know you've connected safely. On Apple devices, for instance, it just gives you it just gives you the entire certificate, and you have no way of actually telling if it's authentic because you have to manually check it. I don't know if you remember, but earlier in the year, like midsummer probably, UT, the information security team, sent out an email reminding everyone to retrust their network, and that was because they updated the wireless certificate, and everyone's devices would reject it unless they trusted it again. So it turns out there's actually ways of tricking clients because they don't do this correctly. So you can get past the TLS protections because TLS isn't implemented properly. But if you trust TLS, then the whole system should work. Right. So this is a more detailed diagram of the back and forth that happens. So in the first step, you establish a TLS tunnel, and then you carry out the Microsoft protocol, and then you close it out. So at the end of this whole thing, there's a key that's created with TLS, and that key is used as a pairwise master key for your connection. So every single client will generate a different TLS key, and so they'll have a different pairwise master key. So after EAP runs, then you go into the four-way handshake, and then it's WPA2 as described before. So this is an example also captured. So this beginning section is using EAP, and then so you can see that some identity information is sent, and then TLS gets set up, and then the access point sends its certificate, and then the client validates the certificate, or it should. This is a step where a lot of client implementations have problems. And then the TLS handshake goes through. And then at this point, this application data is where the MS-CHAP protocol is being carried out. It's a very hairy protocol, but it's a lot of floof. Really, it's broken. And then after that, you get a success message being sent back. That means the server has authenticated the client, and then the access point and the client use the key from the TLS session as a pairwise master key to do the four-way handshake. And after that, you have a PTK and a GTK appropriately set up, and you've authenticated via WPA2 on like an enterprise system. Oh, okay. So I don't have time to go over the MS-CHAP v2 break, but there is a fantastic talk by Moxie Marlinspike that goes over it in a lot of detail. Yeah, I think, yeah, that's the end of this talk. If there's any questions, especially over the crypto stuff, because I kind of went over that fast.